He graduated in 2012.
12.
Yes. And he's a postdoc at Ohio State, and he's been doing a lot of research on indirect detection of dark matter and also the distribution of the dark matter in the halo. And today, welcome back, and he's going to tell us about the gamma ray probes of the substructure of dark matter distributions. Thanks.
Thank you very much. So it's very exciting for me to be invited back so quickly. It's a lot of fun to be here and to tell you about the new work I've been doing for about the past year or so. So I want to tell you about how we can probe dark matter substructure in the universe and why this is very interesting. And so just a brief outline, I'm going to talk about what I mean by dark matter substructure and how dark matter distributes itself throughout the cosmos. But how do we probe it? So I'm going to try and convince you that indirect detection is the way to do that, and then I'll explain what I mean more precisely here. So indirect detection really is if all the dark matter out there in the universe is annihilating with itself, especially in the densest regions where it collapsed and is very dense, and maybe it annihilates to gamma rays that you can see. We have gamma ray detectors that can pick that up, and maybe we can see it amongst all the other gamma rays that are being produced in the cosmos. So what I want to do is give you some examples of how we can probe substructure through the intensity spectrum of the gamma rays that we see. But also I want to spend some time to talk about how the anisotropy of the gamma rays that we see can have a lot of information about how dark matter is distributed and how we can use that information effectively. And this is works of a lot of collaborators here, including Bhaskar, and I'm very thankful for all the help. Dark matter only simulations show us how dark matter starts very smooth with some small perturbations in the density. It will eventually collapse gravitationally. And we have simulations that give us a distribution of dark matter that is very similar to the distribution of galaxies that we see in galaxy surveys. And if I want to do an indirect detection signal, what's important are the densest regions, and that's given here. So this would be what it looks like, say, very early on, where you have all these filaments, but you also have these nodes here. And that's where the densest regions are, and these are what we call halos, dark matter halos. And if I look at just the halos, this provides a very good description of the cosmos, and this is where the galaxies live. And so this looks very similar to a picture of galaxies that you might see. And
so when you're talking about the halo, you're not talking about a galaxy halo, you're talking about halos in general as a place where galaxies form.
Yes. Yes, that's what I mean.
Dark matter halos. It's dark matter only situation.
Right.
So there is no
So I'm describing, yes, so we have the formation of dark matter halos that form.
But, so when you're thinking about halos, you're not thinking about a single galaxy, you're thinking about a cluster size, or you're thinking about a couple of galaxies?
So there are many different sizes. It's actually an ensemble of halos. So there are halos that are galaxy cluster size that have thousands of galaxies within them. And then there are halos that have a single galaxy within them. And so there's a range.
But when you're talking about a halo that has multiple galaxies in it,
Yes.
each of those galaxies also have their own sub-halo?
Sub-halo in that sense, yes.
Okay, so
That's
when you
true.
say halo, which do you mean? Or do you just sort of mean both?
When I say halo here, in this description what I'm showing, I'm thinking of what some people call field halos that are just the main halos themselves. And without
Okay, so you're not thinking individual galaxies, you're thinking about the broader universe structure halo.
That's right.
Okay.
That's what I'm describing here.
All right, and when you're talking about substructure, you're talking about substructure of the universe, not substructure of individual galaxies.
No, so here we go. Good question. So what I'm going to talk about when I talk about substructure is each of these halos then, each of these dots may look something like what's shown over here. And this is a simulation of a single halo. And it has, as you mentioned, all these little sub-halos within it. So here in the center you can see the diffuse main halo density, quite smooth in the center, and it goes less dense as you go further out. And then the further out you go, the more and more of these sub-halos that you find populated within the halo.
Is the thing in the middle a galaxy, or is it or are we looking at a cluster of galaxies?
Good question. So what you're looking at here is dark matter only density plot of a dark matter halo.
Okay,
And
what's
so
the
this-
size scale here?
The size scale here would be about 200 kiloparsecs radius, so probably 400 kiloparsecs across.
So this is certainly not a single galaxy size.
So that's the size for, say, the Milky Way. And so the Milky Way is about 30 kiloparsecs, and the Milky Way halo resides right in here. But our halo goes out much, much further than
The
than
halo,
galaxy.
right. I'm thinking about the disk. Sorry.
Okay,
All right, so
good.
this is a galaxy size, and what you see is substructure, dark matter substructure within the galaxy, and that's what you're talking about.
No, so
Yeah,
the- within the halo.
Within the
Yeah,
halo.
Yes.
Okay.
Yes. So the galaxy resides in the center, and then the substructure's further out, much, much further out. Okay, good. So this is the picture here. This is the prediction from a dark matter only simulation. Okay, and it's predicting a lot of substructure. And so if each of these dots has a lot of substructure, actually then you get a lot more annihilation within the centers of each of these substructures. You get a lot of brighter annihilation signal. So when I'm going to try and predict a gamma ray signal from annihilating dark matter, the amount of substructure matters a lot, and this is a big problem in trying to do predictions. This is actually very important to understand. So here's another picture from the Aquarius simulation of a similar halo, and they have similar results. The substructures themselves can have substructures, substructures, and on and on. And then you can have streams from mergers coming in, and those can also be substructures. So subhalos are one type of substructure, but also streams, caustics. There are lots of different types of substructures. And so it could be difficult to explain. So early on as well, so what's important then is, well, this only goes to a certain resolution, but how small can these structures become? And early simulations, if you go down and down to smaller, higher resolution, at some point, the properties of the dark matter will create a cutoff in the power spectrum. It's not scale invariant perturbations all the way down to infinitely small scales. There is at some point where there's some free streaming of the dark matter that will prevent certain sizes, wash out certain perturbation sizes. Also, if dark matter should have some coupling with itself or some coupling to baryons, you can have acoustic oscillations within the medium, and that could also wash out scales below a certain size. And so some sort of physics here is going to set some smallest scale of perturbation, which will then form some smallest size structure, smallest size halo. And those will merge, and the smallest subhalos then will be formed out of these guys. And so how small the substructure mass function goes can play a big role as to how bright the annihilation signal can be.
Is the assumption that these halos, once you get to your smallest structure, are going to be spherically symmetric, or are these things something where you worry about you get vibrations and oscillations and?
Yeah, so in reality, they are not necessarily spherically symmetric, but initial models will model them as spherical for now. But you can add to the models the different distributions of the sizes. They tend to be more ellipsoidal in general. Okay, and how this first collapse tends to happen is you do get these really small filaments within the large filaments, and then out of that you get these small structures, and then you have these subhalos, and then they start merging, and they form bigger and bigger structures. And the question is, how much do they disrupt and feed into the main halo? How many survive and stay as actual substructures? But there's more. Now, what happens when we add baryon physics and galaxy formation? How does that necessarily affect things? So there's evidence that there can be destruction and evolution of substructure from supernova feedback and radiative feedback. If there's an active galactic nucleus, a black hole giving off jets, these shocks passing through structures dark matter, even though it's only gravitational, it can disrupt and affect these structures. Also, ram pressure stripping is very interesting. Let me explain here. So here's actually a very recent video from the FIRE project by Hopkins et al. And what this is showing is a similar scale. Sorry, it's hard to see. But what you have here is those initial the initial collapse there seems to be disrupted by the first supernovae, and then you get a lot of mixing here. Sorry, on the left is density map, on the right is temperature of the gas. And you're getting these huge flows, but you see eventually at around Z of 100, you finally get galaxy forming, but you still have these huge flows going out. Now this is an environment that is has a lot of late mergers, is more active than our Milky Way galaxy, but it gets an idea of the kind of effects that they do observe. You have to have these galaxies scale cold flows to see the right mixing of metals and to get the right properties of stellar populations that they see today. And so can these things affect cold dark matter? So these are new, we're understanding more and more, so that's still being debated. Ram pressure stripping is also an interesting phenomenon in that it can remove gas from the substructures. So the subhalos often will have, say, small subhalos could have, around the Milky Way, can have galaxies within them. Some of the largest subhalos house dwarf galaxies. So some of the dwarf spheroidals that we see are some of the largest subhalos around our Milky Way. And there's concern that we're not seeing enough of them. And so this is from the CLUES project, and it's trying to simulate our local group. And here's the Milky Way galaxy here. And in this particular scenario, they see a formation of a sheet of structures that actually, at early times, passes through the Milky Way. And the effect of that, they call ram pressure stripping. And so this video shows on the left dark matter, on the right gas. So here the Milky Way is forming, and you see lots of substructures, but here comes that sheet, and you see on the right with the gas, just strips off all the gas, but the dark matter is surviving. And this affects the formation of dwarf galaxies within many of these substructures, and quenches star formation. And so these substructures can be there, but they don't have stars, and we just can't see them. So ram pressure is also something that exists and makes things difficult. Yes?
How come those sheets?
Okay.
I mean, normally what you see is things collapse along different dimensions, like they first start three-dimensional, then become a sheet, and then the sheets become filaments.
Filaments, yeah.
Good. That's actually pretty cool. I think I've thought about that before. Your two sheets that collide. Do you think that's common?
No, I don't think it's a universal thing. There is evidence, like when we compare the Milky Way galaxy to, say, M31, and you compare the substructures, M31 seems much more normal.
I agree.
And so maybe the Milky Way is just weird for some reason. Maybe it's because of some event like this. It's hard to say. It's hard to say.
Simulation?
So this is the CLUES project?
Yeah.
Yes. So they have a website with lots of pictures and okay. Okay, but wait, there's more. So yes, so of course we want to see substructure because that can inform us, like, are we understanding the predictions properly? Is the baryon physics correct? But there's all this dark matter phenomenon that we don't understand. If dark matter should be warm dark matter, that means small mass, so that it collapses later than cold dark matter does. Then that suppresses star formation of structures, and the small structures don't form. And so this side is again from the CLUES project, where they tried this with warm dark matter, and on the large scales, so galaxy halo, dwarf galaxy halos, they're indistinguishable. You can't tell the difference. But it's when you get to the smaller structures that you can see that they're very, very different.
You have a question, 100% wrong.
This one would be 100% warm dark matter, yes. There can also be multi-component dark matter. So different kinds of dark matter, different masses, right? That would also give different predictions. If there's the self-interactions of the dark matter, this can affect the density profile of the substructures, for example. And so there are a lot of things that, a lot of physics that we may be able to probe if we can see substructure. And so there's a lot of good reason to try and do that. But how? How can we, it's there, or it should be there. We predict that it's there. But how could we see it? And so it's hard to see, possibly with stars, especially if you're smaller, a halo smaller than a dwarf galaxy-sized halo, so smaller than 10 to the 10 solar masses, you're not going to make stars. And maybe you're not holding very much gas. So it's just, you can't see it with a telescope, maybe. Gravitational lensing, there's a lot of studies now showing that strong gravitational lenses are affected by substructure. And so we may be able to probe some models, but we would need a large sample of lenses. And right now we only have maybe a dozen or something. So we want to find a whole lot. But this could be very, very difficult. So it could be that the most direct way to probe small-scale structure is indirect detection. And but what can we learn from it? So the indirect detection signals that are affected by small-scale structure is the extragalactic diffuse signal, so the gamma rays coming from the cosmos. We can look at nearby galaxy clusters like the Coma cluster or the Fornax cluster, and they would be predicted to have lots and lots of substructure. Or within our own galactic halo, so we look out into our halo and there would be lots of substructure there. So these are the main places we'd look. And so we don't have a signal yet, so there are two scenarios for how this could play out. One, that structures are so strong that they're responsible for us finding indirect detection. So I'm going to give an example of that. Or it could be that substructures are washed out for whatever reason, through dark matter physics or baryon physics, and there isn't a lot. Then if we see dark matter annihilation in some other region without much substructure, such as the galactic center, but we don't find it in the diffuse, then we can start to constrain models of substructure. And so I'll give an example of that as well. So just to review briefly how this intensity from indirect detection comes about. So if I'm looking in a direction, I integrate along the line of sight, and the dark matter annihilates to photons with some spectrum here. And this will tell me how many gamma rays I get per annihilation. And it's the square density along the line of sight that I matter. So I add up what's the square density here, what's the square density here, and I add all those contributions up. And that determines the rate of annihilation. And then there's some opacity here. If the gamma rays are very high energy, they'll interact with CMB and extragalactic background light, and they'll be, so we'll lose some of those gamma rays. And what also determines the rate is how strong the cross-section is. And so here we're going to assume a constant annihilation cross-section times relative velocity. And then the mass here. So what's important is the number density squared. So you have an inverse mass squared here of the dark matter particle. Okay, so given, this is general, given any density map, I can take the simulation and I can calculate the intensity in different directions from annihilation.
So this is just sort of a simplifying set of assumptions. The assumption is basically you've got some effective cross-section. It's not terribly energy dependent. It's always going to photons. You're not worried about any other interactions, that there's one and only one species, et cetera, et cetera, et cetera.
So the only assumptions I think I'm making here is, yes, the constant sigma b is one big assumption. But here, this is general. So you're right, there could be different species of dark matter, so I would sum this for each species of dark matter.
So that would just, in some sense, go into your effective sigma. So what you've just got is some sigma effective, which includes your branching fraction, summing over all of your different species, et cetera.
Yes, I have a total effective annihilation rate with a total effective
All right, this is a good
spectrum.
way. Okay.
Yes, that's right. Okay, good. So what we really need then, what we can take model from the halo model is what's the mean value of the density squared at each redshift. And this is where the substructure can really make, this is where the substructure comes in. If there's lots of substructure, the mean square density is a lot higher at each redshift on average. But we can't measure it precisely by itself because we don't know what this cross-section is. So the mass, we can, if we see something, we can determine the mass by seeing what the energy of the gamma rays are. Okay, so we get that. But without knowing what the cross-section is, what value this would take, we have no way of untangling what the amount of substructure is, just by itself. Now, so if I'm...
You're actually kind of blown away by just the ratio of sigma v over m squared.
Well, so the m, like I said, the m
Yeah.
we can extract from, if we see a signal, we can extract the mass from the energy of the photons that we at the signal.
Okay,
we're seeing.
right, that'll, okay.
So that'll take out the
Yeah,
m. So yeah, the m we can determine, but there's no way to really extract sigma v. So there is this degeneracy between the cross section and substructure effect. Okay. Now, if I'm looking at annihilations just locally, so from a nearby galaxy cluster or within our own halo, then I don't have to integrate over all redshift. This reduces at redshift 0 to this expression here, where we have this energy piece by the spectrum, and we have this J factor, which is the line of sight integral over density squared. Okay, so this J factor then contains the substructure, but so we still have the sigma v J factor degeneracy. Okay, so that's the big problem. How do we deal with that? So the first example is where the substructure impacts discovery. And here I'm asking the question, for example, take one of those things where substructure matters. So how about a nearby galaxy cluster? So if I look at a nearby galaxy cluster, like the Forex Cluster, could substructure make that much brighter than, say, the galactic center? And the galactic center is considered going to be a bright source. We're very close to it, only 8 kiloparsecs away, and it's very dense. Just how dense is up for debate, but which I'll describe. But it is very dense and it's very nearby, so that's a good place to have a bright source of annihilation radiation. So to consider this question, I needed some models of substructure. So I took 3 models from the recent literature of substructure that appeared. And so one here is based by Gao et al. In 2012. It's based on this Phoenix simulations, which is actually a galaxy cluster size simulation. So it's good for applying to a galaxy cluster, but they also took information from the Milky Way sized simulations, the Aquarius simulations. And so they gave a fitting formula for the surface intensity due to substructure. So I can apply that directly. There's a very nice, second is a very nice model by Kamienkowski, Kushiapis, and Kulin. They use a density probability distribution function. And they took their model and they fit it to the Via Lactea 2 simulation, which is a Milky Way size simulation. But now this had to be scaled up to galaxy cluster size. And Sanchez-Condi et al. Suggested a way to do that. And so I'm taking their model. And then there's a third model by a group that studies galaxy clusters, by Pinsky, Frommer, and Bergstrom. And they fit a double power law to the substructure intensity profile in Aquarius. And then they also scaled to galaxy cluster size. And all these models normalize to a minimum subhalo mass of 10 to the minus 6 solar masses. Now, just for fun, there are models that go down to, say, as low as 10 to the minus 12 solar masses. That's pretty extreme, but they are out there. And so I'll try that as well, just to see what the effect of a very low minimum mass would be. Okay, but I want to compare this to the galactic center. And we have some degeneracy there as well. So how we understand the profile of dark matter, the dark matter density profile, is, well, there are several ways. But one is through looking at tracers, so masers and stars and molecular gas, and seeing their motions, and determining what the gravitational potential is there. And then what some groups are doing are assuming a profile with some parameters. So for example, the NFW profile here is a common choice. And it has two parameters here, a scale density and a scale radius. And then they determine what values of these parameters are consistent with the tracers that they have seen. And Catino and Julio did this in 2010. And they did it also with an Inastro profile. And Nesti and Salucci also did it more recently, came up to similar results. And they also did it for a Burkert profile, which is a chord profile. So NFW and Inastro are cuspy profiles. They become very, very, very dense at the center. Whereas the chord profile will increase like 1 over r for a while, but then will flatten out and become like a constant density chord at the very center. Okay, so if I look at calculate what the possibilities are, here are the J factors. So remember, the J factor had the line of sight integral of the density squared, so that has the effect of the substructure. And so these are the results from those, what parameters are allowed for these profiles from those papers. And so the cuspy profiles do go to quite large values of the J factor, but the Burkert profile is actually quite a lot lower. And these are all consistent so far with the kinematical tracers that we've observed so far, apparently. And so it could be that the galactic center could be a lot dimmer if it's a chord profile. Well, how does that compare to the Forex Cluster, which is much further away? And so I'm looking at a certain angular scale in the sky. So if I'm looking at a certain distance from the center of the galactic center, or a certain distance, angular distance from the center of the Forex Cluster, I'm looking on the same angular scale. And so here, Forex Cluster goes to a radius of about 3 degrees, 6 degrees diameter in the sky. And that corresponds to about a megaparsec, with it being 20 megaparsecs away. So here you can see I tried it for 3 different profiles. And if you look at the smooth halo J factor, they're very similar. So the density profile, particularly at the center, doesn't seem to affect too much, but it's really the substructure models that make quite a difference, especially further out. So it extends the density profile, which goes out almost constantly out to its virial radius before cutting off. And then if you look at the extreme example here of a very low mass minimum scale for the substructure that might survive, it can push things up quite a lot, to up to 1,000 almost, J of 1,000, which is much larger than the galactic center. So Forex Cluster is an example of a nearby galaxy cluster that's in the southern hemisphere, same as the galactic center. So there are experiments, many, many experiments that are looking at the galactic center. So it's very simple for them to just point also to where the Forex Cluster is and apply the same analysis to seeing if they see any sort of signal. Okay, so I'm going to go on to another example here where discovery instead constrains substructure. An example of so what if annihilations were observed, say, at the galactic center, where there's not much of effect from annihilation, from substructure, but you don't see it anywhere else. And an example of this is the 130 GeV gamma ray line that was a bump in the data observed by Fermi. And so it's been seen at the galactic center, and they looked everywhere else, and there's no sign of this line in the anti-region of interest. So if they focus on the galactic center, they see it. If they look at the rest of the region simultaneously, they don't see it. And there's some indications that this could be due to an instrumental effect. It's not necessarily a real signal. For a big reason is that it's actually too narrow of a line. Their energy bins here are 1/3 of their energy resolution, so any line should go over at least 3 energy bins. And this is just too narrow. It's 3 times too narrow. narrower than their PSF. So it doesn't look like a line signal, but they saw a similar line, a similar effect in the Earth limb where gamma rays hit the Earth's atmosphere and give off some gamma rays. And so they can see gamma ray source coming from the Earth's atmosphere, the edge of the Earth's atmosphere, when they look back at the Earth. And that should be smooth, but they do see a bump there near 130 GeV. But it's smaller than can explain the signal, smaller amplitude than the signal that they see at the galactic center. So that's strange. They did discover some reconstruction inefficiencies just below and above 130 GeV, so that may be what's causing this. So they're doing a new pass, pass 8 reconstruction of events that will take care of those inefficiencies, and we'll see what happens to this. But if I take it, say, as an example, so say this were a real signal, and we didn't see it in the extragalactic, what does that say about substructure? Should we have seen it already if there is any substructure at all? So here's this mean density squared, and this black line shows how this, so it's as a multiple of the, so okay, this is the mean square density as a multiple of the mean density squared in each redshift. And so you can see the effect of clumping of dark matter over just being perfectly smooth is a big effect, at least 1 million. So if you just did smooth halos without any substructure, you get this black dotted line, dashed line. If you, we apply this Kamienowski-Kuchiapis model, and that shows this blue line. And if we ramp up, and that's like a low substructure kind of model, but if we ramp it up to be more like the Gao model, then it looks, it could be something like this. And so the lower the minimum mass of the dark matter goes, the larger it gets. Now, if I were to compare this, so substructure can have quite an effect here. If I compare to the J factor for the galactic, and I'm looking out into the halo, I'm looking at the diffuse gamma rays. I'm looking through the halo, so I see the halo substructure, as well as the extragalactic, so I have to add both of them. Well, the effect of the halo, so let's see, here the dotted line shows just the smooth profile of the J factor as a function of the direction I'm looking. So 0 degrees, I'm looking straight at the galactic center. 180 degrees, I'm looking straight away from the galactic center. And so for the diffuse, we're looking at high galactic latitudes, probably around 90 degrees, straight up out of the galactic disk. And here, this is the effect of the large substructure model. And so there's not much, the large substructure can have an effect, mainly a few. That's because most of this is due to the galactic center. Because we're so nearby the galactic center, it's a bright source, and we're far away from the substructure. So this is an effect of our position within the halo, that the biggest effect is from the galactic center. But we do get substructure effects further out. Okay, so if I were to do the 130 GeV line for some cross-section, the small low substructure model might look something like this here. And you see the two components here in the black dashed lines here, the galactic and the extragalactic signal. And you add those two together to get this blue line. And with the high galactic signal, you get a line signal that looks like this. And here, this is Fermi data of the diffuse gamma ray background. The green lines are the published data, and these pinkish data here are preliminary data from the Fermi Symposium in 2010. The line here is their best fit from the first release. And so if we take that as, we can't overproduce this line, then we can see what is the limit on our substructure model. And so if I look at a particular different cross-sections, remember there's the cross-section, and then there's how much substructure we have. The gamma ray line to be produced with the right amount to produce the right amount of intensity is given by this green area here. And if the line produced all of the gamma rays at 130 GeV that with that power law line, you would get this cut here on the mean square density today. And that corresponds to certain minimum values at the high substructure case and the low substructure case. So it looks like the low substructure case doesn't really probe it, but the high substructure case, there really isn't much probing of it. So we probably wouldn't have seen it in this kind of scenario. But if you can say that, well, we could probably resolve see a line eventually if it made, say, 10% of the flux of the gamma rays at that energy. So then if you can say for sure yes or no, I don't see it, I do see a line, I don't see a line that's 10%, then if you don't see it, then you actually rule out all the substructure models for the high sigma V case, and at the low end, you're actually probing quite a few, 10 to the minus 6 for the low substructure case, or solar mass, minimum mass substructure, the high substructure case. And so for this model, we're actually saying some things that not seeing the line is inconsistent with having lots of substructure and it being from dark matter. So we can start asking these consistency questions. Okay, so I want to move on to talk about another complementary approach to these spectrum ways of probing substructure, and that's by looking at the anisotropies of the gamma rays. And so the Fermi Gamma Ray Telescope is making very nice pictures of the gamma ray sky. Here in galactic coordinates, here we have the galactic emission you can see out in the front. And then lots of fluctuations at high galactic latitudes. So when Fermi tries to characterize the angular power spectrum, or the anisotropies, small-scale anisotropies of the diffuse gamma ray sky, they first need to block out the galaxy. So they put a huge mask, plus minus 30 degrees, to block out the galactic emission. But you can still see some of the emission coming out, leaking out here. So that certainly has some effect on the large-scale anisotropies. But we'll see how it doesn't affect. Well, the other thing they do is you can see these red dots, these point sources, and so they put a 2-degree mask over every point source in the Fermi point source catalog. They use the first year Fermi catalog here. And if we want to see, okay, so what are characterize the fluctuations here? The way to do it is to, well, here the angular power spectrum, you would take the absolute deviations from the mean of the intensity, and you would break them up into spherical components. And L here corresponds to the angular size, and M corresponds to different modes of oscillations at that size. And so to characterize fluctuations of a given angular size, irrespective of what my spherical coordinates are, I can average the square of the coefficients over all the modes of that angular size. And so this gives a measure of the amplitude of fluctuations on that angular size, irrespective of rotations. What's more helpful is what people are calling now the fluctuation angular power spectrum, where instead of the absolute deviation, you look at the relative deviation of the intensity. And so to differentiate, I'll put a twiddle over this angular power spectrum, and it's defined the same way. Now this is useful because if I'm looking at, if I wanted to characterize the angular power spectrum of just dark matter annihilation, say, from nearby dark matter, so anything at redshift 0, then the value of this becomes independent of energy. It actually becomes a function of just the J factor. So because the distribution in the sky is the same at each energy, it's the same emitters in the sky, and so you get the same picture. If I were to take a picture and you looked at the distribution of the fluctuations, they would be the same at different energies. Why that doesn't work for extragalactic is because if there's a continuum of emission, I can have something far away emit, and that's redshifted, and then that mixes with something that's emitted here, and so that mixing from far away emission to nearby emission will change, will cause us to modulate with energy. But if I'm looking at just nearby emission, then this is a constant, and the dark matter substructure within our halo has a particular value for this angular power spectrum. Okay, so that's independent of energy. Okay, so that's a couple details here. When I want to measure angular power spectrum, if I have a source that's purely isotropic, the same in every direction, and I start collecting gamma rays from that purely isotropic source, I will measure a non-zero angular power spectrum, and that's called shot noise. But that will decrease. The more gamma rays I collect, that angular power spectrum will decrease, and that shot noise generally goes like 1 over n, 1 over the number of gamma rays that I receive. Okay, so this is always subtracted from the measurement, and whatever is left then is your signal that you're looking for, and you're hoping is different from 0. Now, if I have multiple populations of things emitting, so I have some pulsars that are emitting gamma rays, but I also have dark matter, and I know the angular power spectrum of one, and I know the angular power spectrum of the other. I can just add them to get the total angular power spectrum. But to go to fluctuation angular power spectrum, sorry, wrong button. To go to the fluctuation angular power spectrum, I just pulled out a factor of intensity, and that got squared here. And so this is related to this by a factor of intensity squared. And so all I need to do is normalize everything by intensity squared. And this is how different populations add in fluctuation angular power spectrum. So what's really important here is if I have a population of dark matter with some value here, and I have some background emitters with some value here, what matters is the relative intensity of each of those. And what's really interesting is I can look at some energy where there's only some background emitter, and there's no dark matter. And then I can look at another energy where all of a sudden there's dark matter, and it wouldn't have to be very bright if this C due to dark matter is much bigger than this one. It wouldn't have to be very bright to actually start to see a signal. So it really depends on what the relative values of these fluctuation coefficients are. Okay, so if I want to see if I can see something, I need to know what's the statistical error of angular power spectrum that I see. And when n is small, actually the error is mostly due to the fact that there's shot noise. And we say our measurement is shot noise dominated. And it's actually proportional to the shot noise, so it goes like 1 over n. But it also, the most important factor here is the sigma b, the angular beam width. So this is the angular resolution of the experiment. So the better angular resolution I have, that brings down my statistical uncertainty of this fluctuation angular power that I measure, the total value. Eventually, that will saturate out, and you end up with a constant error. And so in this regime, you're shot noise dominated, but eventually you'll become in a saturated regime, and it would take Fermi decades at multiple hundreds of GeV to not be shot noise dominated. It's just not receiving enough events. So we're always shot noise dominated for the Fermi experiment. Okay, so this is what Fermi has measured. So what they do is they take an average, a weighted average of the angular power from 155 to 504. And why did they do that? Well, so they applied it to the data that they showed directly, and then they did a galaxy subtraction and looked at what that did. And you're not very confident about that we understand the galaxy emission very well. But they do a galaxy model subtraction, and what they found is it only affected the multiple bins below 155. But above that, at the these are the small angular scale bins, and they weren't affected at all. So it seems that the galactic emission really only affects large scale fluctuations. So they throw those away, and then they average these over all 4 energy bins. So they only looked at 4 energy bins to increase their statistics. This is only 10 months of data. And they got a very significant, non-zero measurement for the fluctuation angular power of what they see. It's consistent with constant. It's consistent with being from some unresolved emitter, a single population. And look at this amplitude. It's of the order 10 to the minus 7. Sorry, 10 to the minus 5 steradians. So very, very small amplitude. And that's a bonus. So for background, angular power is very, very small. That's actually much smaller than what we'd expect from dark matter substruction, which we expect to be about 10 to the minus 2, perhaps. Then we can maybe see it very, very easily. So notice they only went up to 50 GeV. That's as far as they had data. So they didn't look up to energies high enough where you might expect 100 GeV wind, for example. Okay, so this is what you might see from dark matter. This is from an Inesto smooth halo profile of our galaxy. This is from the fluctuation angular power from the Aquarius simulation, what they saw. And then these are various ones from the extragalactic. And so these are very small. And so this is actually what dominates. This is mostly due to the cusp at the galactic center, the angular power here. And we masked that out. So actually, this gets killed by the galactic mask. And so, but this power on small scales is very much what we'd be expecting to see. So we could be very sensitive to the galactic substructure. And this is a schematic of how that can go. So if I have some dark matter annihilation from halos that looks something like this. So this is the emission of the gamma rays that they see. And there's some model of what in the background, some blazars or some other gamma ray emitter. And so then that might go like this after you take into account the opacity. Then the total measurement would follow this black line, like this. But they could have another model of the blazars. We don't understand the blazars all that well, the population. So that could be very consistent with blazars, even though in this region we're completely dominated by the dark matter signal, for example. But then if we go to the angular power spectrum, so this is the angular power of the blazars and the angular power of the subhalos. And so when you look at where there's no dark matter, you just get the value of the blazars. But once you turn dark matter on, then it becomes more and more closer to the subhalo angular power. And you get this huge modulation that just sticks right out. And so that takes away this difficulty of seeing the signal, a smooth signal over with a smooth background. Okay, so we're in a similar situation here where the background, whatever it is, the emitters, they're at some low value, but our subhalos are at a much higher angular power. And this is what I see from the angular line. So here's the same picture I showed with the intensity. And so for these two models here, here's the Fermi data, and this is their best fit constant value. And so if the substructure angular power is up here, this is what this is what the line would look like. And we can see, now it's hard to know how big an error bar is going to be over here. But this is the low substructure case. And now if I want to talk about the size of the signal, I'm going to measure it with respect to the size of the error bar. So they maybe measure a signal up here with some error bar. How high is that above my expected background? And I would say so many sigma. So when I say this is a 1.5 sigma bump, I'm not talking about statistical significance because I haven't done a study about the underlying statistical distribution of this observable. But what I'm just talking about is the size of the signal. And this is maybe then a 10 sigma sized feature. Okay, so that could stand right out. Fermi should look, probably.
So they have data, right, for this?
Yeah, the data is there. Yeah. They have, I think they're doing an analysis with 4 years of data, but they have 5 years.
Yeah, TAMU probably is doing the angular anisotropy. Like he wants to that he's doing
With the gamma rays?
yeah.
So he was involved with the first. I would assume he's continuing his involvement. Yes. Yes. Yeah. So Ichiro's not a member of the collaboration, but they bring him in to help out with analysis. Yes. Okay. So the question is then. Well, one interesting thing here is you get a huge signal here, but only when we have a huge signal here. So to be honest, we would have seen this. We didn't need the angular power spectrum, right? And likewise, maybe even the small bump we would have seen. And it actually turns out that for Fermi, if you see, you would see probably a small bump here and nothing here still. So it looks like the hint would be in the intensity still first. But for discovery, or for a basic, well, you're probably going to want anisotropy. And so what can we say? Well, is there a case where the anisotropy would be more sensitive than
So this arc link effect and all this stuff would be in an isotropy scene. Like the background.
we wouldn't be including the Earth limb.
because it's-
Right. So that would be outside the range. Okay, well, so just to remind you, for flux, if I don't see a signal, then statistically it's a Poissonian observable, and so I constrain the ratio of dark matter to the total, the ratio of the flux of the dark matter to the total flux to be 1 over the square root of the number of photons I received. Okay, but for angular power, this ratio ends up being the square root of the uncertainty of the angular power, which also goes, well, so this uncertainty we saw goes like 1 over n when we're shot noise dominated. And divided by the fluctuation angular power. So we want, to be sensitive, we want large angular power, as you'd expect, and small uncertainty. Okay. So here you get that angular power will be more sensitive to the spectral line. And this is at the 1 sigma level for a 1 sigma size signal, given this condition here. And okay, so this, remember the uncertainty went like 1 over n, but in the numerator was the angular resolution. So you want higher angular resolution and large angular power. The other thing that's interesting is, so remember signal strength I'm just defined to be the signal divided by the uncertainty. So number of sigmas. So the uncertainty for the flux goes like 1 over the square root of t. But the uncertainty, the uncertainty for the anisotropy goes like 1 over n, is going like 1 over t. So it's shrinking like 1 over t. So the number of sigmas of a signal with time grows much faster. And so this is what I was saying, where maybe for reality you get the first hints, 1 sigma hint from the flux given by the dotted line, but the discovery could be from the anisotropy given by the solid line. All right, so the anisotropy eventually just takes over. Now gamma 400 is another experiment due for launch right now in 2018. It's a much larger instrument, and so it's designed to observe much higher energy events. And its current design says that in the region of overlap with Fermi LAT, it has 10 times the energy resolution and 10 times the angular resolution. So the angular resolution of about 0.1 degrees. And it's the angular resolution. So it has 5/8 of it has a smaller effective area, 5/8 the effective area. So overall, the energy resolution effect helps both signals simultaneously. But you don't get much of an improvement in the flux measurement. But the anisotropy, the added angular resolution, makes this very, very sensitive to anisotropy. And you would discover this Fermi line almost immediately with gamma 400. And so I don't know if they know this yet, but gamma 400 is the perfect anisotropy machine. And so we'll see if they realize that. So this comes into now complementary searches using flux plus angular line, angular searches. And so we're showing this for the line. If I'm looking at a small, again, a hint signal, say only a size of 2 sigma, Fermi-LAT after 1 year, so similar to the data we got, should have been able to probe this area space here, where this is the substructure boost of the substructure over the smooth J factor. So the higher the boost, the brighter. So this is basically how bright the substructure is as a factor. And this is the substructure angular power. And so the flux only probes a certain substructure boost, but the angular power spectrum is given by these vertical lines. At high angular resolution, angular power, it can probe down to smaller fluxes or to smaller substructure brightnesses. And so here you can gain a little bit from angular power if it's bright enough. But after a certain amount of time, the flux, you can't really do much better than the flux limit here. For gamma 400, it would cover after 5 years, it would cover the whole parameter space. It should have seen it. Even if there's no substructure, just the halo, it should probe to at least 2 sigma. But it's the strong signal. It's the 5 sigma where the angular power spectrum really adds a lot. So at 0.03, it can push you down a little bit for the Fermi-LAT. But I mean, in the 5-year data, it's not giving you much extra, but it can improve. If there is something there, it can actually push you from a 2 sigma sensitivity to the full discovery. Gamma 400, you really want to do angular searches. Okay, it adds a lot. It probes a lot more parameter space. Okay, so that's example 130 GeV line. This, of course, should be applied to lots of other things. So to conclude, substructure content of dark matter halos it's a very active research topic right now. It's sensitive to particle dark matter properties. People are seeing it has consequences for self-interacting dark matter, warm dark matter, and so on. But also galaxy formation processes that are very complicated are needed to be understood, and it can give us information about them as well. Indirect detection may be the most direct probe of substructure, and the constraints, though, will require discovery, and that discovery then depends will depend on the mode of discovery as well. Galactic center, diffuse, nearby galaxy cluster, those will be very different situations. The intensity spectrum tells us about how much dark matter clumps, that square density. Anisotropy spectrum gives us independent information on galactic substructure, and it's complementary to the intensity. Thanks.
Questions for Sheldon?
So if you have your, so you said game of annihilation cross-section rho square. So as we were discussing, so if your annihilation cross-section has some weird velocity dependence and all this stuff, so all this correlation could be changed, like angular power spectrum versus intensity for a given signal.
So you mean correlations between?
Because sigma v is suppose is a function of velocity. And
Yep.
suppose at low velocity it goes up, all this stuff. So now velocity is small. So again that means that now your anisotropy and flux correlation is different.
So yes, when that happens,
So
this value here is what we measure is the gamma ray, the angular power spectrum of the gamma ray.
Mm-hmm.
And I'm saying, right now I'm saying that's directly the angular power spectrum of the substructure. But as soon as you couple to the velocity distribution,
Mm-hmm.
that's no longer the case,
Yeah,
right?
so-
The particle physics now matters as well. And so this can then become not just astrophysics, but it can be astrophysics plus particle physics.
But do you know how would it change? Like any idea, like how this say,
Okay, so if we did say, there are different cases, right? So is the cross-section increasing with velocity or decreasing with
It sounds
velocity?
increasing, of course.
Okay. So if it's increasing with velocity, then, right.
So my question is, would this sequel also increase the same way as I'm thinking about the intensity will increase? Probably it would still increase, but then velocity distribution is throwing me off. Like how do I think about that?
Right.
Because it's a different integration.
I'm trying to think of what the best indication would be
Yeah,
to see something like that. I think maybe the first clues would be by observing cluster collisions or something like that. But
Because why I'm saying that, because substructure is an additional uncertainty.
yes,
But that's also an additional uncertainty I can put in. So
yeah.
now
So we can
how
model
I
that.
would- yeah, exactly.
We can
How
model
I
it
would
and
extract
then
what- yeah.
extract what the effect would be. So because substructures are smaller potential wells, right? I don't expect that they increase the velocity dispersion as much as, say, at the galactic center. So again, I think I'd have to think about it. Think about exactly what the effect is. It's competing effects,
Yeah,
right?
yeah, I know. So,
Between the
like,
gravitational
yeah,
velocity and
exactly.
dispersion and the density. So you make the faster regions are the areas actually with the smaller densities, right? So there's that competing effect between density squared and faster velocity dispersion. And, I think density squared still wins, but I'd have to think about that.
Other questions? Anyone else?
First one, I'd like to maybe just make it clear, is constrained off in the direct, or lack of direct detection experiments on the cross section. Does that relate at all to the self-annihilation cross section?
In general, not necessarily. There are relations. There are relations,
Right.
but it's model dependent. So again, you can take certain classes of models and relate them, and people do, and then they probe annihilation cross sections based on direct detection experiments based, with those assumptions. So they do that, but it's easy to get around those.
It's very common, that's just some.
Yeah.
All right, I'll just ask one quick one. So if I go the other way, following up on Casey's,
Yeah.
the velocity distribution of your dark matter would presumably depend on the mass of the dark matter, but also I'm guessing would be very different inside these substructures than in the halo, than the whole structure. Do you have a sense of how much that velocity distribution would change? Or said differently, if it is very different,
Yes.
are we sitting in a substructure, and how much would it change from the typical assumptions that people are putting in
Could we
for the
measure that?
direct detection models?
It's a question people are asking
Okay.
right now, very, very much. And I don't think I can give a good answer. I haven't studied the velocity distribution within substructures. I would tend to think of them as the usual NFW kind of distributions, already a settled system.
But you also need baryons now.
Well,
Any galactic disk, yes.
Yeah, because then those are adding interactions to the whole game.
within our galaxy, yes. Yes. So, on the one hand, we don't expect that many substructure objects this close in the galaxy, but again, if there are small,
So, all right, so
small
we're sitting
concentrated
in a
clumps, then-
smoother halo because we're in the
Yes.
disk, is the assumption.
And,
Because we're closer to the center.
Wait again?
I'm trying to find X who's not detecting at the detection experiments.
I don't know, I mean, in some sense,
Halo, the velocity is will be much smaller.
Yeah, I mean, let's say, right, if the velocity distribution is different than what people put in,
Mhm.
and I'm not an expert about what velocity they put in, because of structure effects, then it may well be that all of the limits that we are quoting are not anywhere near what we think we're quoting. Or vice versa, and it may be that we are already much closer to the neutrino lines than we think we are.
So he's talking about whether we are Maxwellian or not.
That's right, yeah.
Yeah.
And actually, they're
And
They're,
does it?
they're changing the formalism now to take into account that we don't know what the velocity distribution is, and so there's what's called a halo-independent formalism. And what it's doing is it's showing how much velocity distribution can change. So what velocity distributions are possible, and how much can it change the constraints? It can change the constraints, yes. Can it make all those regions that are intersecting aligned to be one region? No, they have not been able to find any velocity distribution that can do that.
Also, don't worry about those neutrino lines because you know the neutrino background very well.
It's
You can subtract it.
well, but the question is how close are we to them, right? I mean,
Yeah.
those lines, in some sense, those are neutrinos. I know where they come from. Those I believe. The question is the limits scale up and down depending on the velocity distributions where we've made assumptions. And so if those velocity distributions are in fact different because of where we reside in the disk and in the relative halos and our local interactions, those could all go up or down.
That's a very important fundamental question for direct detection, yes.
And you don't have a sense of how they would change in general inside the center of structures versus substructures and versus
No,
the general.
unfortunately, I don't think I do.
I mean, because if
But I
it's a
think-
factor of 2, that might be interesting. If it's a factor of 100, that might be very interesting.
Right.
And if it's a factor of, something tiny, who cares?
Yeah, Louis was telling us that it's non-Maxwellian,
That's right.
but again, he was saying basically baryons. So-
Yeah, the baryons screw it
That's
up.
right, yeah. He's waiting for those simulations to be done too. So what's interesting with is that if they can get stars to form properly, which it looks like they're starting to do now, then we can actually have some more confidence and see what substructure looks like within that environment.
Plus I always have these crazy ideas that, the flux from the sun affects the baryons inside the greater solar system, in the heliosphere, which could in fact blow dark matter out, in which case we're not swimming in any dark matter because it's basically been pushed outside of the heliosphere, in which case we're not in the game.
Great.
I can't write down the equations that would do that, but there are days that I wake up and I say, we're not swimming in it. We're swimming in neutrinos, but we might not be swimming in dark matter the way we think we are. All right. Interesting.
Well, if no more questions, let's thank the Sheldon again.